We can now shift our discussion to talk about geometric sequences. Each term in the sequence of a geometric sequence is obtained by multiplying the previous term by a fixed quantity. The multiplier is called the common ratio. So before, in an arithmetic sequence, we saw that we added the same number to each term to get the next term. Here we're going to be multiplying each term to get the next term in the sequence. When faced with the problem involving sequences and series, your first question to yourself is this a geometric sequence or series, or is this an arithmetic sequence or series? In red at the top, I've got an arithmetic sequence. Why? Because look, 5 minus 3 is 2, 7 minus 5 is 2, 9 minus 7 is 2, 11 minus 9 is 2, 13 minus 11 is 2. We say that this is our common difference, D. Difference means we subtract. So then you can conclude, okay, we have an arithmetic progression, which could also turn into an arithmetic series. If we have this one in blue here, 4, 12, 36, 108, then 12 divided by 4 is 3. 36 divided by 12 is 3. 108 divided by 36 is 3. We have this common ratio of 3. The ratio of this divided by that is the same as this divided by that is the same as this divided by that. Alternatively, how could you think about this? If our common difference in an arithmetic sequence is 2, that means we're adding 2 each time we take one of these little bunny jumps. Plus 2. Plus 2. And similarly, we can think, well, if this divided by this is 3, then we're multiplying by 3 here. Times 3. Times 3. Times 3. To find the nth term of a geometric sequence, we use this formula. U to the n equals u1 times r to the n minus 1. The exponent on the r, and only the r, is n minus 1. Where u to the n is the nth term we're interested in, u1 is the first term, and r is the common ratio. For example, for this sequence, 4, 16, 64, 256, 1024, find the 53rd term. Well, the first thing we have to do is determine that it's a geometric sequence. 16 divided by 4 is 4. 64 divided by 16 is 4. 256 divided by 64 is 4. 1024 divided by 256 is 4. Or we could think of we're multiplying by 4 to get there, to get there, to get there, etc. So if we have that common ratio of 4, we do know that it's a geometric sequence. Sequence because I'm not adding, I'm just having commas there. It's a list of numbers. Find the 53rd term. I know my formula is u to the n equals u1 times r to the n minus 1. U to the n is u to the 53 equals, my first term is 4, so I plug that in, times my common ratio is 4 to the n minus 1 is 53 minus 1. If you're going to go out to the 53rd term, you're going to have to jump 52 times. How big is each jump? It's a jump of 4. That's where that formula is coming from. And where are we starting? At 4 as well. So you can see as we plug these numbers in, we get a huge number, 8.11 times 10 to the 31. Here's a first example using geometric sequences. A geometric sequence has a fifth term of 3 and a seventh term of 0.75. Find the first term, the common ratio, and the 10th term. Well, we know un equals u1 r to the n minus 1. We have to know that formula. And it tells us that the fifth term is equal to, well, the fifth term will be u1 r to the 5 minus 1, which is 4. It says that's equal to 3. And the seventh term, which will be u1 r to the 7 minus 1 is 6, is equal to 0.75. So we've got two equations and two variables. Our algebra skills are good, so we know how to solve this. Let's solve in equation 1 for u1. u1 r to the fourth equals 3. Divide both sides by r to the fourth. We'll get u1 equals 3 divided by r to the fourth. Well, if that's the case from equation 1, let's substitute now to equation 2. Here's equation 2. u1 r to the 6 equals 0.75. Let's now substitute for u1, which is 3 over r to the fourth, times now r to the 6 equals 0.75. r6 over r4 becomes r squared, so we have 3r squared equals 0.75. Divide both sides by 3, and we wind up with r squared equals 0.25. Take the square root of both sides, and we get r is equal to plus or minus the square root, r is equal to plus or minus 0.5. Well, I go back here to u equals 3 over r to the fourth, and I plug in. It doesn't matter because I'm to the fourth power. Both negative and positive will give me a positive answer. And I find u1 is equal to 48. So I've done the first two parts. I found the common ratio, which could be plus or minus 0.5, and our first term, which is 48. Now that we know that our first term is 48 and our r could be either plus or minus 0.5, we just have to substitute into this equation here because we're looking for the 10th term. U10 is u1, which is 48 times r when it's positive, 0.5, to the 10 minus 1 is 9, gives us 0.389 to three significant figures. And u10 is equal to 48 times minus 0.5 to the 9, which gives us negative 0.938 to three sig figs. Here's another problem using the geometric sequence. Find the number of terms in the geometric sequence 0.25, 0.75, 2.25, etc., 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 all the way out to 44,286.75. So what the problem is, we don't know this n. We don't know what number term this is, but we do know our formula says un equals u1 times r to the n minus 1. What is u1? It's our first term, 0.25. 0.75 divided by 0.25 is 3. 2.25 divided by 0.75 is 3. So we can conclude that r is 3. So let's substitute for u1 and r. 0.25 for u1, 3 for r. We still have n minus 1. But we know that the nth term is 44,286.75. So we set our nth term equal to this, and we can now solve this equation. Divide both sides by 0.25 and we get 3 to the n minus 1 equals 1,177,147. Take logs of both sides and use the power rule for logs, which says we can move this out front, and I get n minus 1 log 3 equals log of that big number. Once that is completed, let me just get that focus there. Once that is completed, we can divide both sides by log of 3, and then add 1 to both sides. And when you do that math out, you get n is equal to 12. That's the 12th term is the answer to this problem. Here's an example with a geometric sequence. A car originally worth $34,000 loses 15% of its value each year. First part A says, write the geometric sequence that dictates the year-by-year value of the car. Well, first we have to know the formula. It's un equals u1 times r n minus 1 to the exponent n minus 1. So if we start with $34,000, that is our first term of the sequence, or u1. Times, well, r, if we're losing 15% per year, we start at 34,000. 15% less is 28,900. 15% less is 24,565. 15% less is 20,880.25. You can see that each of these, if we represent this, the price with the bar graph is getting less and less and less. And each drop here is 15%. The drop from this height to that height is 15%, which means that this height is 85% of what we started with. That's why our r is 0.85. If you did this divided by this, you get 0.85. This divided by this is 0.85. This divided by this is 0.85. That's what our r value is. It's our common ratio to the n minus 1. So we've done this first part. We have written the geometric sequence. Find the value of this car after 6 years. Well, we already know our equation for the geometric sequence, so we just want to plug in 6 for the year. And that will dictate, this goes to 6 minus 1. And when you figure this out on your calculator, you get 15,085.98 cents. After how many years will the value of the car be below $10,000? We know our geometric sequence is this from the previous parts of the problem. We want to know when will this geometric sequence, let's call it equal to 10,000 so we don't have to deal with the inequalities. Well, the first step would be to divide both sides of this equation by 34,000 to get 0.85 to the n minus 1 is equal to 10,000 over 34,000. Because I have a calculator, I'm not even going to simplify that. I'll take the log of both sides. So with my power rule of logs, I know that I can move my exponent out front. So I move my exponent out front. And the next thing I do is I divide both sides by the log of 0.85, which gives me log of 10,000 over 34,000, all divided by log of 0.85, which gives me n minus 1 is equal to 7.53. That's how many years after how many years will the value of the car be below $10,000? N minus 1 equals 7.53. You might ask yourself, why didn't we solve for n? Well, remember, n minus 1 is the number of times you're jumping, and that represents the number of years later. So the question still remains, why solve for n minus 1? Let's take a look at our geometric sequence. 34,000, 28,900, 24,565, 20,880.25. This was our U1. Here is U2. Here is U3. Here is U4. Each time we jump, we go 1 year later. So we go 1 year later, 2 years later, 3 years later. Look at our n is 2 and we're 1 year later. Our n is 3 and we're 2 years later. Our n is 4 and we're 3 years later. Well, what is this jump? This 1 year later, 2 year later, 3 year later? It is n minus 1. 3 jumps to get to n equals 4. So if the question is, after how many years? We found it was n minus 1 was 7.53. That is representing the how many years later. That n minus 1 is the number of jumps in blue, or how many years later. So if they ask you for how many years later, we're not solving for the nth term, we're solving for the number of jumps. Here is a geometric sequence example. The number of people in a small country town increases by 2% per year. If the population at the start of 1970 was 12,500, what is the predicted population at the start of the year 2010? Well, we know if it's a geometric sequence, we have u to the n equals u1 to the r to the n minus 1. And it would seem straightforward that you would plug in 12,500 for u1, and your r would be, well, if we're increasing by 2%, that means we're 100%, which is what we had to start the year, plus 2% more, which gives us 102%. Well, 102% as a decimal is 1.02. That's the first tricky part, that you have to interpret 2% as 1.02. Now here comes the real tricky part. What are we looking for? U to the what? Well, if we start at the beginning of 1970, we go 1970 is U1, 1971 is U2, 1972 is U3, 1973 is U4, 1974 is U5, 1975 is U6, etc., 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 all the way down into 2010, which will be U41. So at the beginning of 2001, we have U41, which means we took n minus 1, 41 minus 1 is 40 jumps. To go from 1970 to 2010, you need to go forward the number of years, which is n minus 1, 40 jumps. That will leave us at U41. That's the key, because we're going to go 41 minus 1 is 40 jumps. Well, when you plug this into your calculator and solve, you get 27,600. The key here is you first have to know that 2% increase is 1.02, and that if we're going to take 40 jumps, then we're from U1 all the way out to U41, and our exponent here is n minus 1 is 40.